I haven't done Java.
It's more tedious writing.
It's much easier to see because almost everything for you.
Python, I find.
Yeah, Python's easier than Java.
I think
Python's the
I love
easiest,
Python.
is the easiest.
I've never learned. My first language was whatever it was that
I just like the ability to say, well, you wanna pass through there and make
Sure.
You wanna return 5? Okay. You wanna declare something and then change the size of it and then that things and make more, Python doesn't matter.
My first language was Visual Basic, but after that it was Java. It was Python integrated into Java. Yeah, it was really fun though, because it sort of had everything broken up into its own little methods. And then it was like practice, and you could call those methods. It was the whole entire language was just calling methods. There's nothing else you can do other than calling methods, passing values in return. Directly in call.
For you, don't say I gave you anything there, except for an also. You just messing with me?
Yeah, I just see that. All the time, that's for my students. Well, no, I wasn't sure if I should just grab it now or wait for it to come by the line. It's all right there.
His display ability.
Don't judge me if I cover
No thanks. I see how that worked during the exam.
First time I actually ripped it off, I was like, this is weird. I feel like I couldn't tell the difference between
You gotta take them off.
Let me just stop there.
Take them off. This one came in.
You see it?
I think I found it. There you go.
Thank you.
Maybe. Sure.
That's on my seat. It's over there now.
Thanks, sir. Turning these things in sometimes.
Do you know Marcin?
Do I know Marcel? Maybe.
Oh, he's a Polish guy. He's from Poland.
Maybe. I probably remember him if I saw him.
Okay, he's a friend of mine. He said hi.
Oh, okay. Now I feel bad. Okay, so. We don't have to, but we're going to start into our next portion of the course where we do direct proof. And today we're going to focus on the easier types of direct proof, although I don't necessarily know if there's anything as easy as anything that has proof in it, but hopefully you guys will see that it's not too terrible initially. Okay, so about the next month we're going to be studying methodologies of proof: direct proof, indirect proof, inductive proof. Okay, so yeah, proof. So sorry about that. I might have said this before, but in case I didn't, this portion of the course is going to be a little bit more difficult than the first portion, so sorry, it's just the way it rolls, okay? And then the assignment number 4 is going to be due on Monday, and all that stuff's going to be the direct proof stuff that we're doing recently, okay? And I do have your guys' examinations. I'll give them back at the end of the class, and then I think I posted the solutions. If I didn't, somebody yell at me. Okay, good, so I did. Good stuff. Okay. I I don't know if that was helpful or not, because you might not have remembered what you wrote down. So I'll give those back to you guys at the end, and then if you guys have questions for me, make sure you ask, okay? In general, they were very good, so I didn't have any problem, I don't think, with anybody's, well, mostly anybody's. I'm just messing with you, Donnie. All right, so questions before we get started, guys? Okay. So what we're going to do today is we're just going to get an overview as to what direct proof is and try to do some of the direct proofs. But basically, direct proof is a method to prove universal statements that we can't utilize exhaustion for, okay? On the examination, I did have a question to where I asked you guys to prove something, and it was fairly easy because you could exhaust everything, all right? I want you guys to consider, don't write this down because I don't know if it'll be helpful or not, but sum of two evens is even, okay? So, think about this, guys. Somebody throw out two even numbers to me.
4 and 6.
4 and 6, okay, so 4 plus 6 is 10, which is even, right?
Yes.
Last time I checked, okay? Somebody else throw out two more even numbers.
6 and 4.
6 and 4. Somebody who's not a jackass, throw out two more even numbers that are not the same as what we already
12
got.
and 16.
12 and 16, which is 28, even, all right, two more. Now everyone's afraid. What is it?
2 and 8.
2 and 8, okay. And you guys get the idea that it looks like that no matter what two integers that we add that are even, it's going to be even, right? Now, what's the problem with trying to prove this?
Currently, we know exhaustion.
Oh yeah, currently, the only methodology we know to prove a universal conditional statement is by exhaustion, right? And how many pairs of even integers could we come up with if we really wanted to?
Infinity.
Infinite, right guys? So, we have an inkling it's true, right? The problem is how do we prove it? And that's what we're going to be doing for the next portion of the course. How do we prove things that we think are true, okay, or we have a good idea that are true, but we don't necessarily know how to do it by exhaustion, okay? So, I just wanted to go through some basic definitions, and then I'm going to show you guys like some of the algebraic technique necessary. Then we're going to go through the direct proof stuff, okay? So, I know we already went through some of these things already, so. So we know what an even integer, right guys, is if we see z even, okay, we know that that just means that we're looking at an even integer. And this is the definition that we want to be interested in, okay? If you see that n is equal to 2k, that means it's an even integer, right? Like for instance, guys, the number 10. 10 is equal to 2 times 5, right? So that means it has to be even, okay? The number 28. The number 28 is 14 times 2. That means it's even, okay? Every even integer contains a factor of 2. That's the definition of even, okay? No matter how you write it. The definition of odd is that it's equal to 2 times an integer plus 1, okay? So, somebody throw out a nice easy odd integer for me. 3, okay? So, 3 is equal to 2 times 1 plus 1, okay? It fits the form. Somebody else throw out a nice easy odd integer, excuse me.
7.
7, okay? 7 is equal to 3 times 2, or I'm sorry, 2 times 3, it doesn't really matter, plus 1. Every odd integer can be written in that format, okay? So that's the definition of odd. If you can't write an integer such that it's 2 times an integer plus 1, it's not odd, okay? So we're going to be seeing that's the definition. So guys, do we understand the definition of even and odd, okay? That's what we're going to have to utilize. And that's for every single even or odd integer, okay? Perfect square, okay? Perfect square can be written in the form of something equals k squared, okay? And that's really easy, right guys? You've been doing that all your lives. Like for example, if I had the number 81, that's a perfect square because it's 9 squared, right guys? Okay? That's the definition of a perfect square, okay? If you can find some number that when you square it, it equals that number. Or in other words, the square root of that number, okay? All right, one of the most important definitions we're going to be using is this thing called integer closure, okay? When we talk about closure, okay, closure means that if you perform an operation, it's still in the set of that numbers, okay? So, let's say for instance, if you added 2 integers, okay? Like for instance, if I added something like 130 plus 75, okay? 130 plus 75 is 205, which is an integer, right guys? So it looks like if I add two integers, the result is an integer, okay? The same could be true of subtraction, right? If I do 130 minus 75, that's going to be 55, which is an integer as well. If I multiply two integers, let's say I take 130 times, not 75, 2, because I'm lazy, that's 260, which is an integer, right guys? So addition, subtraction, and multiplication are all closed by integers, right? That's what we mean by closure. Well, why not division? Why is division not closed?
Oh, rational, it could be rationalization.
It could be a rational number. Could you guys give me an example of two integers when you divide them, it doesn't give us an integer? 4 and 3. Perfect, okay? 4 over 3 is not an integer. So closure is not extended to the set of integers over division, okay? So, does that make sense, guys? When we talk about closure, if you add, subtract, multiply, square two integers, okay, it's all closed under integers, okay? So, if I added two arbitrary integers, I know that I get an integer out of that. If I subtract two arbitrary integers, I get an integer, multiplication, okay? So, I just have some basic examples. It just says to show, it doesn't say to prove. Andre?
Is this just for integers?
There's
So
other
is-
sets
is-
as well.
Okay, so I mean, is this rule of closure, is that just set to integers? Or
Not
is it-
necessarily.
Okay,
Like for
we're
instance,
just working with integers.
right, for right now, we're only working with integers,
So you're
okay?
saying it's the sum or the product of these two integers is equal to an integer?
That's correct.
So it has to stay the same type of number, is that what you're
Correct.
saying?
Basically like a data set, okay? Like when you define variables, okay? Like if you define like an int plus an int, you get an integer output, right?
Right.
If you define float plus float, you get a float output. However, if you do float plus int, you guys get what out of that?
Float, right? It is.
It always truncates
Depends on
into
Oh,
it.
yeah.
Depends on the language.
Right, okay, never mind, okay, you're right. I was thinking because most of you guys either do C or C++, but yeah, it depends on the
C?
language. Yeah, with C, it'll go out to an integer, so it just truncates all the float stuff. But regardless, for right now, we're only dealing with integers, okay? It actually is true for rational numbers, okay? And for those of you guys that have to suffer through linear algebra, you get to prove more of that stuff. But for right now, it's just integers. Okay, anyway. So let me show you guys like just a few examples of where we can show a specific number or even a specific structure to be even or odd, okay? So 37 is an odd integer. You guys know this, right? Because 37 is equal to 2 times what number plus 1? 2 times 18 plus 1, okay? It fits the form of an odd integer. So if I ask you guys to show me that 37 is odd, that's how you do it, okay? Does that make sense to everybody, guys? Not difficult. If I asked you to show me that 2x plus 4 is even, that has to be equal to twice some integer, right guys? But we don't know what x is, okay? So does anybody think they might know how to show that that's even for any value of x?
Take the common,
Okay,
two
because there's a
common.
factor of 2 in there, right? So if you factor out a 2 as a greatest common factor, some nasty algebra here, what do we get, x plus 2 in there?
Yeah.
Okay, so that's by factoring. We don't know what the value of x is, right? But what do we know about the domain of x? It's an integer, right guys? What is 2? Integer.
Okay.
So we have an integer plus an integer, which
Closure.
means that we have an integer by closure, right guys? Didn't we just say that by closure, if you add two integers, you get an integer? So that's some different integer, right? Like maybe y, maybe p, maybe q, maybe theta, maybe zeta, whatever letter you want. Let's just call it 2n, where n is an element of the integers. Okay? If you want to define n as equal to x plus 2, you may, but you don't have to. Okay? I can see that by transitivity, x plus 2 is the same thing as n. Okay? As long as those are integers. Okay? So we're just going to justify these steps. We're going to say this is by factoring, and this is by closure. You don't have to put integer closure because I already know that 2 and x are defined as integers. Okay? And right there, what we've done is we've proved that for no matter, well, we haven't proved yet, but we've shown no matter what number of x you plug in there, it's gotta be even, because it fits the form of 2 times an integer, okay? So does that make sense, guys? Any questions about how you guys might show that a structure might be even? Basically contains a factor of 2. Okay? Now, what about this animal? Okay, we have our 6y plus 8x plus 7, and I need to show that that is odd. In other words, 2 times an integer plus 1. All right, suggestions? Sean?
6y plus 8x plus 6 plus 1.
So
Factor
usually-
out the 2.
Nice. So usually 7 is 6 plus 1. Now how come 7 is not 5 plus 2 or 4 plus 3? How come 6 plus 1?
Because you have
You
to
didn't
have,
want a plus 1, so you could prove it.
We
to
need
the-
a 1 out of that. Nice, okay. So let's rewrite this. 6y plus 8x plus 6 plus 1, okay? Nobody doubts that 7 is 6 plus 1, right? Oh boy, that would be bad, okay? We'd be SOL at this point in the course. That's just by computation, right? And then as you suggested, we can factor out a common factor of 2, not from everything, but from just those first 3 terms, right guys? So we would get twice the quantity of 3y plus 4x plus 3 quantity plus 1. Okay. That's just a GCF. Nobody in here doubts that, right? We all know algebra 1. Might not be common core algebra 1, but okay. And then finally, guys, what do we know about 3y plus 4x plus 3? It's an integer, right? It's 2 times some integer now, right guys? We don't care what the values of x and y are. We define x and y to be integers up here, okay? Just like a computer program. If you add a bunch of integers together, the output's going to be an integer.